Hello everyone, my name is Owen O'Donnell. I'm a Product and Marketing Manager at VIAVI. Quantum safe networks are a hot topic in telecoms today, and with 6G around the corner, what will be the impact of quantum encryption? This is the topic of today's talk. Let's begin with four important definitions. Firstly, Q-Day. Q-Day, also known as Y2Q, or the quantum apocalypse, refers to the hypothetical point when quantum computers become powerful enough to break the encryption algorithms that currently secure the internet and digital communications. When this day comes, quantum computers could break today's encryption algorithms, which are widely used for securing websites, emails, VPNs, banking, etc. No one knows the exact date. It could be 5 to 10 years away, or it might already be happening in secret. Governments and tech companies are already publishing roadmaps to migrate to quantum safe to prepare for this eventuality. Definition number 2, HNDL, harvest now, decrypt later, also known as handle or also known as SNDL, store now, decrypt later. These are attacks occurring now where bad actors intercept and collect encrypted data today while it's still secure under current cryptographic standards. Then they store that data long term until quantum computers with enough power become available to break today's encryption, allowing them to decrypt it later. This is particularly worrying for government communications, military and defense sector, financial transactions, and medical records. So that brings us to definition number 3, post-quantum cryptography. PQC refers to cryptography algorithms that are designed to be secure against an attack by a quantum computer. Unlike current encryption methods, which rely on mathematical problems that quantum computers could solve efficiently, PQC uses problems that are believed to be hard even for quantum machines. Organizations such as NIST in the US are busily working to standardize these new algorithms to allow the migration to take place. And finally, crypto agility. This is the ability of a system to easily switch between post-quantum cryptographic algorithms without a major re-engineering. And this is critical for responding to new cryptographic vulnerabilities or regulatory requirements. So data encryption affects everything we do, and as a result, everything is going to be impacted. We don't often get a technology change that affects so many transactions and so many verticals. According to a Capgemini Research Institute report, nearly 2/3 of organizations globally are concerned about the risks posed by quantum computing and are already actively considering or preparing for post-quantum cryptography migration. Looking at this list of just some of the daily events and devices which will be affected will open your eyes to how big this is going to be. Everything from online banking, accessing corporate files over VPN, digitally signing for a mortgage loan, downloading an app, IoT device reporting, to very serious concerns regarding military communications and government directives will be impacted. An encryption key is a string of specifically organized bits designed to unscramble and decipher encrypted data. Encryption keys today are a certain length or number of bits, 128 or 192 or 256, but these keys are in danger of being cracked when quantum computers come along. So extra long keys using new algorithms are being developed by organizations such as NIST, which is hoped that they will survive the power of quantum computers. These new encryption algorithms are called PQC. But these extra length keys will bring enhanced security, but a trade-off is that they will have an impact on CPU consumption, memory, latency, and other end-to-end performance metrics across networks, services, and applications. And these concerns are echoed by industry players for example, SoftBank and GSMA, who say when cryptographic protocols are deployed in data transmission infrastructure, they can place a significant load on communications and cause latency problems resulting in poor quality and lower throughput. And GSMA have said it is important for mobile operators and vendors to test whether their current servers can support the overhead incurred by the larger ciphertext and signatures, and whether it is necessary to upgrade to servers that are better suited to the operation's standardized PQC algorithms. So why is PQC migration a big thing? Well, the race to migrate to PQC migration has already started, with finance, defense, and government leading the charge. But the transition won't happen overnight. It could take years, touching nearly every part of IT infrastructure. What makes PQC migration a challenge are one size doesn't fit all. Not all PQC algorithms will work for every use case. Figuring out which NIST-approved algorithm is best to use for different scenarios will need careful consideration, trialing, and testing. Compatibility issues will emerge. Firmware updates may be required, with not all devices being updatable, especially in industrial or IoT environments. PQC algorithms must also work across heterogeneous environments like cloud, on-prem, mobile, etc. And organizations may need to run parallel algorithms, that is, one classical and one quantum safe, during the transition. Performance impact is a big concern for organizations. Ensuring security against quantum computing is the highest priority, but also ensuring no degradation in end-user performance is a close second. Getting the balance right between the computational ability of the device, the security strength of the algorithm, and the performance being maintained is a tricky balance, and one that needs research and thorough testing. For example, a longer delay in performing a banking transaction on your mobile phone might raise concerns that you are being phished and then change the resulting user behavior. And finally, retrofitting encryption across massive systems is such a large task that companies will be dedicating teams to migration projects to perform auditing of cryptographic assets, classification of data sensitivity, enablement of crypto agility, testing hybrid approaches, understanding performance metrics, running pilots, validating compliance against the standards, and staying ahead of the threat by planning for future upgrades. When it comes to standardizing these algorithms, NIST, which is the National Institute of Standards and Technology, officially began its PQC standardization process with a formal call for proposals way back in December 2016. Over the following years, proposals were submitted and candidates then announced, with finalists for standardization selected in 2022. Then in August of 2024, the first three PQC standards officially were published, called FIPS 203, 204, and 205. And in a subsequent press release, NIST encouraged the transition to these new standards as soon as possible, mentioning the risk of store now, decrypt later as being a big concern. When it comes to post-quantum cryptography adoption in the telecoms networks, it is now being addressed. 3GPP Release 20 is considered the final major release of 5G Advanced and a transition point to 6G, addressing PQC adoption. Specification 33.707 has been created and is titled Study on Transitioning to Post-Quantum Cryptography in 3GPP. The goal of this technical report is to determine the necessary security levels and identify the protocols needing PQC integration. Now, this is a technical report or study item as opposed to a specification, but it aims to identify which security protocols will require post-quantum cryptography, assess the impact of larger PQC key and signature sizes, and examine hybrid or standalone PQC algorithm suitability for different 3GPP systems. The GSMA Association, called GSMA, is a global industry organization that plays a central role in the mobile telecommunications ecosystem. They represent the interests of over 1,000 mobile operators and businesses across the mobile ecosystem, including device manufacturers, software companies, and infrastructure providers. And they have already taken a stance in the migration challenge to post-quantum cryptography for telecom operators. They have published a document called Guidelines for Telecom Use Cases, which provides best practice guidelines to support the telecoms industry's transition to quantum-safe cryptography. This guideline addresses common challenges and use case-specific considerations. One area outlined in the document is performance implications, where it says, it is imperative that deployments enter a testing phase to assess the viability of certain post-quantum cryptography algorithms to minimize the performance impact. It also says that the area that will be impacted by the migration will be tunnel setup performance. Adding post-quantum key exchange steps will add some latency to the tunnel setups, both in terms of cryptographic processing and in packet round trips. The document is currently at version 2.0 and no doubt will have a newer version as more challenges and specification requirements come to light. So this is a slide borrowed from a presentation by Vipin Rathi called Quantum Resilient 5G and 6G Networks, which shows the current 5G core architecture on the left-hand side with the functions and interface protocols currently used to intercommunicate. This is before quantum-safe measures are applied. But on the right-hand side is a look at how a post-quantum core might look with all of these interfaces upgraded to be quantum safe with PQ hardening or increased data encryption from AES 128 to 256, which is considered quantum resistant for many applications. So this diagram comparison shows an example of just how much impact quantum proofing the core network will need. So the wireless evolution we are currently experiencing is 5G, which brings enhanced mobile broadband, massive machine type communications, and ultra reliable low latency communication. But as we prepare for 6G, what can we expect? Well, the word we're seeing is extreme. We will see extreme high data rates, extreme coverage extension, extreme low energy and cost, extreme low latency, extreme high reliability, and extreme massive connectivity and sensing. 6G will continue to handle sensitive data across sectors like healthcare, finance, defense, and autonomous systems. Without quantum-resistant security, these systems could be compromised. Operators and vendors should begin preparing for PQC integration by evaluating their cryptographic inventory and planning migration paths. Security teams will need to consider performance trade-offs, especially for constrained devices and latency-sensitive applications. And regulatory bodies are likely to push for PQC compliance in critical infrastructure, aligning with global mandates for quantum readiness by 2030 to 2035. Some of the challenges facing PQC implementation into 6G are performance overhead. PQC algorithms often require larger key sizes and more computation, which can impact latency and throughput. Scalability. Ensuring that PQC works efficiently across billions of devices, including IoT and non-terrestrial networks. Standardization. Global coordination is needed to ensure interoperability across vendors and regions. and bodies like NIST, ETSI, and ITU are leading this effort. And sustainability. Energy-efficient PQC solutions are needed to align with 6G's green technology goals. One aspect needing attention is performance impact of PQC. As the migration efforts begin, many publications are appearing in the form of white papers and reports and press releases and blogs, and one common theme is the concern that these new longer keys may impact end user performance. On screen are just some of these publications and the warnings they sound, such as the waiting time experienced by system users will increase and convenience may decrease. PQC cryptography can cause latency problems, resulting in poor quality and lower throughput. Potential performance and interoperability issues are anticipated, which will require thorough testing. It is essential to continuously test new products and monitor their performance. And deployments must enter a testing phase to assess the viability of certain post-quantum cryptography algorithms to minimize the performance impact. And IT departments would greatly benefit from real-world experiences like benchmarks conducted in real-world implementation scenarios. We at VIAVI conduct PQC performance testing, and our own testing has shown a concerning impact that PQC algorithms can have. Using our TeraVM emulation tool, we tested VPN connections setups with traditional encryption keys, PQC keys, and hybrid keys. The baseline test was a TLS 1.3 session with traditional, that is non-PQC algorithm, and the average setup rate was measured at 65,000 connections per second. We then swapped out the algorithm for a hybrid PQC algorithm, that is a mixture of non-PQC and pure PQC algorithms, in this case denoted by X25519KLCAM768. And we noticed a very large reduction in connections per second setups, down to 35,000, which is a 46% reduction. Then we ran a third benchmark test of a pure PQC algorithm, in this case MLCAM768, which is one of the NIST approved algorithms. And again, we noticed a degradation, this time down to 46,000 connections per second, a 29% reduction compared to the baseline. So this test alone shows why performance test at scale is a requirement before going live with PQC algorithms, so that any impact can be understood and mitigated against. Thank you for watching.